And obviously you get this great attraction there, but again, you're seeing lines along here and along here, along the magnetic field lines. So the little iron filings are basically either being pulled towards it, or those that have a strong enough force holding them back will start to reorient themselves. So not proof of magnetic fields, but give some indication that there seems to be something there that is coming out one end and going into the other. Questions? But I know what you're thinking. You're thinking, this is great, but where are the numbers? Let's do some numbers. The two primary units that you will see when dealing with magnetism are the Tesla and the Gauss. Tesla is the SI unit, Gauss is the CGS unit, both metric. But first off, the symbol for magnetic field, it is a vector, magnetic field. Now, if you look at some more advanced text, they will use the letter H for magnetic field. H and B are directly proportional to each other. They're just different by a constant. I believe it comes from two different groups sort of developing the theory behind it. And one started with an H, the other group started with a B, and it turns out the difference was a constant. So magnetic field, and then the units of magnetic field, the SI units, I guess, of the magnitude, is the Tesla, symbol, a capital T, and then CGS is the Gauss. Which I think is GA. I don't use Gauss that much. To give you some sense of where this stuff comes from, when you're first establishing units, you want to establish something that you hope is global. So that's why the density of water is 1 gram per cubic centimeter, because there's water everywhere, and so you can run the experiments and get close enough results back before the electronics and really fancy equipment. Gauss, the magnetic field of the Earth, is about a half of a Gauss. So it started out with the magnetic field of the Earth as sort of a standard. Now it turns out that the magnetic field of the Earth is not real constant, and this is just sort of an average value. Tesla is a significantly larger value. So 1 Gauss is equal to 10 to the negative 4th Tesla. So if you have a 1 Tesla magnetic field, that is pretty darn strong. That 1 Tesla magnetic field would be 20,000 times stronger than the magnetic field of the Earth. The largest magnet that I think that we have produced is 27 Tesla, somewhere around there. So a Tesla, even though that we will deal with Tesla just because, well, one, it's SI, but also we'll, I might have a problem with the 2 Tesla field, which is a pretty strong field, just because it's easier to deal with numbers like that. All right, so we now have to deal with 3 dimensions. So just a reminder, if I'm dealing with something into the board, or this is out of the board, or out of the 2-dimensional surface, so out of the board here or out of your paper if you're writing notes or tablet. Into the board, or paper or tablet or screen or whatever you happen to be staring at. Cross products, I cross J equals what? Go on, someone take a shot at what letter is going to come next.
K.
Yeah. I hat cross J hat is equal to K hat. This is known as a right-handed coordinate system. So let's just do a quick review of cross products, because cross products are going to keep showing up. Or if you all feel uncomfortable with cross products, we can skip this.
We can review it.
Okay. If I have a vector A and a vector B, and I'm doing a cross product of A cross B, dot products, as you deal with energy and work, dot products deal with multiplying vectors in the same direction. Cross products deal with multiplying vectors that are perpendicular to each other. So if I was doing A cross B here, I'd break A up into components, into a right triangle here. And so this, I'm going to just call A parallel and A perpendicular. And so the magnitude of the cross product is that perpendicular piece times B. If you are dealing with an angle, the angle here is theta. A perpendicular would just be the hypotenuse times the sine of theta. And this would be A times the cosine of theta. So a dot product is AB cosine theta. Cross product, the magnitude is AB sine theta. But cross products do produce vectors. It is a vector product, or sometimes called a vector product, not just a cross product. And as I say, I think pretty much every time for the purists in the group, it actually produces an axial vector or a pseudo vector. But as far as we're concerned, vector works. And if you get into far enough advanced physics, then you'll start potentially caring about the other. So the way you figure out the direction, the vector in the answer is going to be perpendicular to these two vectors. So,
Can you repeat that?
A cross B is going to produce a vector, and that vector is perpendicular to the two vectors you're multiplying. So if I have A and B like this, vectors that are perpendicular to it are either coming out of the board or into the board. And the way you figure it out is the right-hand rule. Anyone left-handed in here? Okay, don't have to worry about that part. Right-hand rule, you put your hand in the direction of the first vector. So A cross B, I put my hand in the direction of A. I got 360 degrees of rotation here in theory. And Then but I want my hand to be oriented so that my fingers, when I bend them, will bend towards the second vector the fastest way. So I point it like that, and then my fingers bend this way, because that's where B is, and my thumb points in the direction of the result. So, the direction of A cross B is into the board. So we now need to add some shorthand notation because this is just handwriting. So if I have A in polar form, we'll just say 3 meters and 60 degrees. B is 5 newtons. Negative 10 degrees. I'm going to set up a coordinate system here. I hat to the right, J hat up. What would be the direction of K hat? Where are you pointing? I cross J equals K. I think a couple of, it's somewhat hard to tell, but I think people are generally, at least, I see 3 people with their thumbs pointing in the right-ish direction. Put your hand in the direction of the first vector, you want your fingers to bend towards the second vector, thumb points out. So if I hat is to the right, J hat is up, K hat is out of the board. Into the board, out of the board. The dot is out of the board, the cross is into the board. Think of it as an arrow. If arrow is being shot at you, you see the point. If it's going away from you, you see the feathers. It's a memory trick, and no arrow feathers are not crossed like that. All right, so A cross B. Well, that's going to be 3 meters times 5 newtons times the sine of the angle between them, 70 degrees. And the direction, well, if I'm considering this is in the IJ plane, A is pointing in that direction, B is pointing in that direction. That's A and B. A cross B is into the board, so negative K hat. And if someone would be kind enough to actually multiply that out.
I got 14.095.
Say it again.
14.095.
14.095.
14.095.
14.095. Negative units. Newton meters, K hat. And the negative we just bring up front. So that would be the cross product between A and B.
Why is it negative K hat?
Because assuming that this, like, I gave sort of the 2-dimensional polar coordinates here. A is this way, B is that way. So A cross B thumb points into the board. And with I hat and J hat defined this way, K hat's out of the board. That's why negative. Questions at this point? When we're dealing with work and energy, what's a Newton meter? Yes. when you're dealing, but that's with a dot product. This is a cross product here, this would not be a joule. It's one of those crazy things about units. Newton meters is equal to a joule sometimes. But we experienced that with torque in the first semester course, even though we touched on it way too briefly. Torque is an example of Newton meters that are not joules. All right. So, I have a magnetic field coming out of the board. Into it, I shoot a proton. That proton will be affected by the magnetic field. And surprisingly, a cross product's about to show up. There is a force acting on that proton that's related to the charge. The bigger the charge, the bigger the force. Related to how fast that charge is moving, and the strength of the magnetic field, and the orientation there. This is the conservative force. But this is the force of a magnetic field on a charge. Is that a question or a stretch?
A stretch.
Okay. Let's stick some numbers into it. I'm going to keep the same convention as right here. So B will make 2 Tesla K hat. The velocity, 3 times 10 to the 8th meters per second. Ooh, that's speed of light. Let's drop that down factor of 100. 3 million meters per second. I hat. What is the force on that proton? Now, obviously, if the proton starts to be affected by it, the direction of the velocity will change. So this is the force on the proton as it enters this magnetic field. We somehow miraculously have the magnetic field confined to this space right here. No magnetic field outside of it. We can get pretty close to this from an experimentalist point of view. We can get pretty darn close to that absolute barrier. All right, so charge of a proton.
1.6 times 10 to the negative 19th coulombs.
All right. My velocity, 3 times 10 to the 6 meters per second I hat. Cross, 2 Tesla K hat. So the math piece of it, the calculator piece, is I'm doing 1.6 times 10 to the negative 19th times 3 times 10 to the 6th times 2. That's the math piece of it. So let's get the math piece out of the way. Around 1 times 10 to the negative 12. Just shy of it.
I got 9.6 times 10 to the negative 13.
Which is roughly what I said. All right, so let's take a look at the units. What are the units?
We're tracking my answers. I said it's newtons.
Does it make sense that it would be newtons?
I mean, it's a force.
Yes. So if you didn't realize it was newtons, and you were pulling the units out of the equation here, what would the units be from the equation?
Coulombs times meters per second.
Don't forget your Tesla.
Density times second.
That's a newton. Yeah, it's gonna be newtons. This is one of the reasons why if you put everything into a particular unit system like SI, you don't have to think through, what is a CMT per second? Also realize that a coulomb per second is an ampere. So this is also an ampere meter Tesla. But recognize, more fun with units, since this is equal to a Newton, a second is a Coulomb meter Tesla per Newton. And this is my intro into probably one of my favorite and worst executed problems I've ever done. The 15 possible multiple choice question of which of the following are units of time. It was really executed because I didn't really think through how long it would take to analyze each one. But it was this type of thing where I have a Coulomb meter Tesla per Newton, which is a second. The more shocking part of it was the number of students who missed the letter S as a unit of time. All right, questions up to here. We still have to do directions. But before we figure out the direction, any questions? All right, direction. What is the direction of the force as soon as it enters into this magnetic field? Here's our coordinate system, if this helps. Ian, what do you got?
Is it just down, straight down, negative J hat?
Yes. The direction, we have I cross K. The order matters. The commutative property does not apply. Does not work here for cross products. I cross K, I is to the right, K is out. So I have my hand to the right, so my fingers bend out, thumb points down, downwards. So, negative J hat.